Douglas,
Yes.
can we start?
Yes.
So the last talk of today is the talk of Douglas Duarte Novaes. He is talking about the averaging method. Please, Douglas.
Okay. Thank you very much, Thiago. I think that let me just share with you if I can't find the chat here. Okay, I have shared it before the link for this lecture. So if anyone can just copy and paste in the chat, for me, I would be very grateful. And if anyone wants to download the lecture notes to follow, feel free. Okay, so just to recap what we have done in the first lecture, we were considering difference equation in this standard form, which are regularly perturbed, non-smooth, regularly perturbed, smooth, non-autonomous difference equations. Epsilon was the distinguished parameter of perturbation, and the main goal was to explore conditions on the perturbations in order that some of the periodic solutions of the unperturbed system persists as periodic solutions for epsilon small distant from zero. Okay, so in order to answer this problem, we used the averaging method, which provides a sequence of functions called averaged functions, which has a nice formula, a recursive formula for computing this function. And the averaging method states that simple zeros of the first non-vanishing averaged function correspond to periodic solutions of our differential equation. So this is the main theorem that we have studied in the first class. So we have L is the index of the first non-vanishing averaged function, and the result states that if Z is a simple zero of FL, then for epsilon sufficiently small, the difference equation admits a uniquely periodic solution satisfying that it converges to a constant function corresponding to the simple zero of FL as epsilon goes to zero. Okay. I have comment before we started talking about the averaging method. I have made some comments about the stability of periodic solutions in terms of the displacement function. So let us recall these comments and adding some more information about it. So we know that the stability of a periodic solution is can be studied by means of stability of a fixed point of the Poincaré map. Okay, we saw that the Poincaré map defined around this periodic solution is given as the identity plus the displacement function. Okay, and by the averaging method, we saw that the displacement function writes as a power series of epsilon, where each coefficient, the coefficient of epsilon power e, is exactly the average function, the average function of order I. We have to define it, this average function, by this. Okay, so in this, under this hypothesis, we see that the Poincaré map writes like Z plus epsilon L FL of Z plus higher order terms of epsilon. Okay, so in order to stud the so in order to stud the stability of the periodic orbit phi epsilon, we have to stud the stability of the fixed point of the Poincaré map. Okay, because if we define Z epsilon equals to the initial condition of this periodic orbit, then we know that it's a fixed point of the Poincaré map for epsilon small. So we can study the stability of this fixed point by taking the derivative of the Poincaré map and studying the eigenvalues of this map, of this linear map, okay, the derivative. So when we compute the derivative of the Poincaré map in the spatial variable, of course, at the fixed point, what we get is the identity plus epsilon L multiplied by the derivative of FL evaluated at Z epsilon plus order epsilon L plus 1. Okay? So since this initial condition, Z epsilon, is given by the implicit function theorem, we know that it is smooth in epsilon. So we know that Z epsilon is equal to Z star plus order epsilon, and this implies that derivative of L evaluated at Z epsilon is equal to the derivative of FL evaluated at Z star plus order epsilon. And this implies that the derivative of the Poincaré map at Z epsilon, epsilon is equal to the identity plus epsilon L times the derivative of FL evaluated at Z star plus high order terms in epsilon. Okay? So let's just rewrite this like this. It's epsilon L multiplied by the derivative of FL of Z star plus order of epsilon, and let's call this matrix now by M epsilon. We saw that if lambda epsilon is an eigenvalue, lambda epsilon is an eigenvalue of M epsilon if and only if 1 plus epsilon L lambda epsilon is an eigenvalue of the derivative of the Poincaré map at the fixed point. So we can study the eigenvalues of the derivative of the Poincaré map in terms of the eigenvalues of the displacement function. Okay, so we saw in the first class, we have to fix something here because I said that in the first lecture, I said that the square of the norm of lambda epsilon is equal to that, but it's wrong. It's not what I mean. The square of the norm of 1 plus lambda epsilon, okay? Actually, epsilon there's this typo here. Okay, so let's use the same idea now, and we see that the norm of 1 plus epsilon L lambda epsilon squared, okay, because now it is, sorry, this is equal to 1 plus epsilon lambda L, let's call lambda star, plus order epsilon L plus 1, where now lambda star, okay, is an eigenvalue of DFL Z star. This is always true when this matrix is hyperbolic. Okay, so if DFL Z star is hyperbolic, and by this I mean that the real part of the eigenvalues is distinct from 0, then lambda epsilon writes as an eigenvalue of, recall lambda epsilon is an eigenvalue of m epsilon. If DFL Z star is hyperbolic, then an eigenvalue of m epsilon writes like an eigenvalue of this matrix plus high order terms in epsilon. This is always true when the matrix is hyperbolic, and this implies that exactly what I have written here. Okay, in this situation, the eigenvalue of the derivative of the Poincaré half map is given by 1 plus epsilon L lambda star plus order epsilon L plus 1. And in this situation, the norm of this eigenvalue is given by 1 plus 2 times epsilon L multiplied by the real part of lambda star plus high order terms in epsilon. And this implies that if the real part of epsilon L multiplied by the real part of lambda star is positive, then this is the square here, then the norm of 1 plus epsilon L lambda epsilon, which is the eigenvalue of the derivative of the Poincaré half map, it's greater than 1. And if epsilon L multiplied by the real part of lambda star is negative, then 1 plus epsilon L lambda epsilon is smaller than 1. This implies that the periodic solution has the same stability as the singularity Z epsilon of the, and now we come back to something that we have defined in the first lecture, of the truncated averaged equation. Okay, Z prime equal epsilon L let me divide it by T, FL of Z, okay? So Z star, since it's a zero of FL, then Z star is also a singularity of this autonomous differential equation, okay? And if it's a hyperbolic singularity, meaning that the real part of the derivative, the Jacobian of this vector field, evaluated at Z star, has a value with real parts distant from zero, then if Z star is a hyperbolic singularity of this truncated average equation, then the stability of the periodic solution provided by the averaging method coincides with the stability of the singularity of this truncated average equation. Okay, so this is what I am stating here, and it's also always true when Z is a hyperbolic singularity of the truncated average equation. Then we can study also the stability of the periodic solutions in terms of the displacement function. Okay, and also the averaging method provides informations under some suitable hypothesis about the stability of the periodic solution. Okay, so let's study now an example where we can apply the averaging method to study the existence of periodic solutions. So let's consider a smooth perturbation of a harmonic oscillator. This one, it's a second order differential equation. B epsilon is a term of perturbation because B epsilon is equal epsilon B1 plus epsilon squared B2 plus higher order terms in epsilon, and G epsilon, which eventually contain nonlinear terms, is also a perturbation. Okay, so it's equal to epsilon G1 plus epsilon squared G2 plus high order terms in epsilon. So the idea here is to find conditions on B epsilon and the G epsilon in order that this differential equation, this second order differential equation, admits periodic solutions. Okay, so some comments before we start in doing computations. This second order differential equation can be transformed in a system of first order differential equations by taking y equal x prime. Okay, so if we take y equals x prime, then x prime is equal y, and y is equal minus x minus b epsilon y plus g epsilon of x y. Note that if epsilon is equal to 0, so when epsilon equals 0, we go to the unperturbed system. Okay, so for epsilon equals 0, the phase portrait of this system of differential equation is given by this. It's just the linear center. So every orbit is periodic. Each orbit is periodic here. So this is just x prime equal y, y prime equal minus x. So for epsilon equals 0, we have that all the orbits of the system are periodic. If b epsilon is positive and g epsilon is 0, okay, then this differential equation has a globally asymptotically stable foci. Okay, it behaves something like that. Okay, then we have an attracting equilibrium at the origin. And if b epsilon is negative and g epsilon is equal to 0, then we have an unstable foci at the origin. Okay, so the idea here is to find functions g epsilon in order to produce limit cycles for this system. Okay, so let us start. Okay, so I'm going to show the steps we have to follow in order to apply the averaging method for studying this kind of problem. Okay, so this is not for this specific example, it's more or less a program that you can follow. And of course, we have some features that are specifically for this example, but this is more or less a general steps that you always have to follow if you want to apply the averaging method to study periodic solutions. Okay, so the first thing we have to notice is that this differential equation is not in the standard form for applying the averaging method. So the very first thing that we have to do when we want to use the averaging method for studying periodic solution is transform our system in order to write the system into the normal form for applying the standard form for applying the averaging method. So what we need, we already have a small parameter, a distinguished parameter of perturbation. This is the epsilon here. We also need that a difference equation which is non-autonomous, because I have already commented that if you apply the averaging method in autonomous system, we eventually can get some periodic orbit, but this is trivial periodic orbit. It's actually singularities, stationary orbit. So it's not interesting because you do not have to use such a technique to detect singularities. You just have to compute the zeros of the system. Okay, so you need, in order to use the average method, you need a non-autonomous differential equation. And more important, as we have stated our theorems, this has to start with an epsilon multiplying everything. Okay, so in this case, let us apply a polar change of transformation in order to write the system, in order to identify a possible new time variable, which will be the angle of the orbits with respect to the x-axis. Okay, for instance, when you travel in an orbit, when the time goes to the future, you change the angle of the system in a bijective way. If you consider that you are in an angle variable, so the angle for the system is a good candidate for a new time in order to write the system as a non-autonomous system. So let's see what's happening here. So let us consider the polar coordinates. Depending on the unperturbed system that you have, you may apply another kind of transformation. Here, since we are in the linear center, the polar transformation will be enough for us. So when we proceed with the polar change, we get r prime equal something and theta prime equal -1 plus a term which depends on g epsilon, and here we call that g epsilon has an epsilon that multiplies everything, minus b epsilon, and the same happens with b epsilon. Okay, and here we also have an epsilon that multiply everything, because we have g epsilon minus b epsilon. So let's fix our domain. D is r0, r1 for some positive 0 and r1 strictly bigger than r0. And note that since it has -1 plus epsilon times something, notes that there exists an epsilon 0 positive such that theta prime is negative for every point in our domain. Okay? So in particular, theta prime is distinct from 0. So we can now compute the variation of the radius. Here we have the variation of the radius with respect to the time and the variation of the angle with respect to the time. However, we can also study the variation of the radius with respect to the angle, okay? And doing this, we get a non-autonomous, one-dimensional difference equation that provides the variation of the radius with respect to the angle, okay, instead of the time. So when we do that, we see that this derivative writes like this, and now we can compute, and it can be done without a problem, without any problem, because theta is always distinct from 0 in this domain. So we can compute this, this quotient. And now, doing the Taylor expansion here, we see that d theta writes like epsilon times something plus epsilon squared times something, starts here and finishes here, and a remainder, a higher order terms in epsilon. Note that we have an r dividing here, but this is not a problem because we are always away from 0. Okay, I'm fixing the domain in order to avoid any problem at the origin. Okay, so this difference equation is a non-autonomous difference equation, is a periodic non-autonomous difference equation because the dependency on theta is always in trigonometric functions. So it's 2 pi t equal to pi, okay? And this writes like an epsilon times a function plus an epsilon squared times another function plus epsilon power 2 to 3 times a function, which is the remainder, where f1 is this trigonometric function, periodic, and f2 is this other trigonometric function. So this transformation allows us to write our initial system, which is a second order differential equation, autonomous differential equation, into a non-autonomous one-dimensional differential equation in the standard form for applying the averaging method. Again, in the next, I think that in Friday I will show an example with another kind of another kind of an unperturbed system, which the things are more complicated. But depending on the unperturbed system that you have, that you are studying, eventually other types of transformations can be employed in order to get your system written in the standard form for applying the averaging method. Okay, so the step 1 is not just apply a polar coordinate transformation. Is apply some transformation in order to transform your system into the standard form for applying the averaging method. This can be hard. This can be a hard task to do. Okay, so this is the first problem that we face when we are trying to study periodic orbits using the averaging method. Okay, for this particular case, pay attention that theta prime is negative. Then in our time rescaling that we are doing here, we are changing the orientation of the orbits. In particular, we are changing the stability of the limit cycles that can exist here if it exists. Okay, so for instance, if for the difference equation 6, we find, let me draw, here's the theta, it's r, we find a periodic solution, which is an unstable one, suppose that is an unstable one, all the orbits are converging to this, then in the original system, x prime, for instance, or x and y, this corresponds also to a periodic orbit, but an unstable periodic orbit. Okay, because I'm changing the direction of the flow when I do the transformation. Okay, so we have to have this in mind. Well, so this is the first step during this lecture. I will come back to this example, and I'm going to avoid this step, okay? Because it always works. So let us concentrate in a more specific example. Let's consider now the nonlinear term of our perturbation given as quadratic function, and see if we can find good parameters here in order that our differential equation, our second order differential equation, has a periodic solution. So what I'm going to do now is just compute the first order differential equation. We know now the exact expression of F1, then I substitute here and I compute this integral. Okay, this is a very direct step. Okay, so step 2, compute the first order average function and its zeros, if any. Okay, so in this case, when I substitute F1, I compute the integral of this function for G1 equal this quadratic polynomial, we obtain that F1 is equal pi times B1 times R. Okay, so this equation, F1 equals 0, has a unique solution, R equals 0. Here we have to remember our domain. Okay, so what is our domain? Our domain is D equal R0, R1, and R0 is strictly positive because we are in polar coordinates. Okay, so we do not have solutions of this equation in the domain. Okay, so this 0 does not correspond to limit cycles of our differential equation. Okay, so we say in this case that the first order averaging method, that is theorem 1 for L1 for L equal 1, does not provide the existence of periodic solutions. Okay, so what can we do now? We cannot apply the averaging method. We can apply the averaging method of the first order.
Douglas, sorry, one
yes,
thing.
Yes, Joan.
This B1, maybe you can explain which is. It's a number that depends on A00 and A11, no?
Sorry?
What
I
is
didn't
B1
understand.
here?
What is?
B1.
B1 is part of our perturbation. This is B1.
Ah, sorry. I forgot that you are considering the trace away from the G. Sorry.
Okay. So in this case, B epsilon and G epsilon are the perturbations of our system, our linear system. Okay. So yes. In this case, B epsilon is just the trace of the linear part of this matrix. Okay. So we cannot apply the first order average method for obtaining.
Sorry again, Douglas, sorry. This is in fact that the quadratic part, as is homogeneous, the Melnikov part function is identically 0, and so does not appear in F1, no? This is the reason, no?
Yes. But anyway, you can just compute the integral of this function and you see that it's 0. The quadratic part does not play any role here. Okay, so what we have to do now, the third step and so on, is to try to apply the second order averaging method. So, however, in order to apply the second order averaging method, take into account Theorem 1, in order to use F2 to detect the periodic solutions of our difference equation, we have to ensure that all the average functions of lower order is 0. In this case, we have to ensure that F1 is 0. We have to assume constraints on the parameter of perturbations in order to have that F1 is identically 0. Okay? So, in this case, what we have to do, the idea here is to assume the minimum hypothesis, okay? Because of course I could just take the first order perturbation equals to 0. However, this is not interesting. I want to keep as much parameter as I can. So I have to assume the minimal hypothesis, the minimal conditions on the first order perturbations in order that the first order average function vanishes. Okay. In this case, what I have to do is to take B1 equals 0. Okay. So this is the step 3. Assume minimal conditions on the parameters of the perturbations in order to ensure that F1 is 0 and compute the second order average function and its zeros. So this is the third step. F1 is equal to 0, as I said, if and only if B1 is equal to 0. And under this condition, if we substitute now G2 here in F2 and compute the second order difference equation, which is given by this expression. Okay, in this case, it's very simple to compute. It's not always like that. Actually, it's usually very hard to pass to the second order average. But here we can just substitute and compute this integral, and we obtain this expression. Okay, so F2 is equal pi times R multiplied by B2. The second order perturbation just appears here in B2, and minus a constant that depends on the first order terms of perturbations multiplied by R squared. So this is important to know, so that when I assume conditions on the perturbations in order to ensure that F1 is equal to 0, this is important that these conditions are the minimal one in order to obtain for instance, the maximum number of limit cycle. Because here, if we have assumed that the first order perturbations were identically 0, then again, we wouldn't have any information about periodic solutions, because this term would disappear, okay? And again, the only solution of F2 equals 0 would be 0, okay? However, but since I'm keeping some parameters, some first order parameters of perturbations, then F2 is now a cubic polynomial in R. Actually, an R times a quadratic polynomial. Then we can use the second order average function that mix first and second order of perturbations in order to obtain information about the existence of limit cycles. Okay, so F2 equals 0 has three solutions, namely R1 equals 0. It does not provide any information for us. R2 equal minus 2 times n square root. This is either negative or purely imaginary, and also does not provide any information about periodic solutions because it's not contained in the domain. And R3 equal 2 times a square root of something, and this is either or positive or purely imaginary. So we can assume conditions on the parameters of perturbation. The condition is B2, A11 multiplied by A02 plus A20. We can assume that this is positive in order that this root is positive, and then it can be contained in our domain. We can adjust the domain in order to contain this root, okay? So applying the second order averaging method, that is theorem 1 for L equal 2, we obtain the existence of a periodic solutions of the differential system 6, such that these periodic solutions converge to R star, which is equal to R3, as epsilon goes to 0. Going back through the change of coordinates, we conclude that there exists a periodic solution of our second order difference equation, x t epsilon, x prime t epsilon, satisfying that the norm of this periodic solution converges to R star, that is, this value as epsilon goes to 0. So here I have provided Mathematica simulation for some specific values of the parameters. Here we have a quite general result because I just have to impose this condition in order to have periodic solutions. Here I am assuming some numerical values for the parameters. Okay, so this is a system that satisfies the hypothesis y minus y plus epsilon multiplied by this quadratic polynomial minus epsilon squared y. And I am drawing this simulation for, I run the simulation for epsilon equal 0, 1. I have also to assume some numerical values for the parameter of perturbation. And in this situation, this limit cycle that appears here is an unstable limit cycle. So I'm drawing the backward trajectories for some initial conditions here. Okay? Well.
So, sorry again, sorry that disturb you, Douglas, but this is the negative solution is because you would like to come back to the planar case, but if you consider the problem in the cylinder, both solutions make sense.
Both solution? What solution?
The positive and the negative one makes sense because you have a periodic solution in the upper side and another in the lower side, no?
Yes, of course. But yes. But it wouldn't appear in this picture, for instance. But if I only consider this difference equation for R belonging to the reals, okay, then we actually would have three solutions, three periodic solutions. R equals 0, which is the one that persists, R positive and R negative. However, I'm studying periodic solutions of this vector field. Okay, so I need to apply a transformation and I need to be careful with the domain of the transformed system in order to make sense with the original difference equation. But you are right. If I'm talking about periodic solutions of this difference equation, 6, 3 those three zeros provides periodic solutions of the differential equation 6. However, it does not, it's not related with periodic solutions of the initial differential system. Yes. Okay, so a second example. Here we assume that the perturbations are quadratic, and for quadratic perturbation, we didn't find any periodic solution in a first order analysis. Okay, so let's increase the degree of the perturbation and see what's happening. Okay, so this is again the first step, compute, transform the system into the standard form for applying the averaging method. And the second step is compute the first order average function and its zeros. In this case, when we have a cubic perturbation, the first order average function writes like this. Just substitute the functions and compute the integral. So we have a quadratic polynomial in R, which has, sorry, this has only two solutions. As I have written here, it's only two solutions, unless I'm forgetting an R multiplying everything, but I don't know. But as it is, there's a negative one.
Sorry, I think that the power 2 in the R in F1 is a 3, maybe, no?
This, I don't know. I think that we have an R that multiply everything. Actually, we have a pi b1 R squared minus a constant R.
It's just because usually when you take an R in front, you obtain a function in R squared. And this is why I think that your 2 is a 3. And then you will have the 3 solutions that you have written. This is because
Yeah. 2 is a 3, but 1 is a 2 here. Right? I think that this is what is happening here. Because you have to have the R, you have to have the zero solution, because it corresponds to a periodic curve. So what's happening here is exactly this, just like before. Okay, anyway, we can substitute and compute the integral, not to be sure. Okay, so in this case we have three solutions. Again, the zero solution, a solution that can in the best situation to be negative, and a third solution that can be positive if you assume constraint in the parameter of perturbations. Okay, so if you assume that this is positive, then R3 is contained in the domain that is well related with the original differential equation that we're interested. And here we can apply the first order averaging method to conclude the existence of a periodic solution of the differential equation 6, such that it converges to R3 as epsilon goes to 0. Okay, so if we go back with the transformations, we conclude that there exists a periodic solution of our second order differential equation, satisfying that the norm of the periodic solution converges to R star as epsilon goes to 0. Okay, so note that if we increase the degree of the perturbation, then we obtain informations about the existence of periodic solution in a lower order of averaging. Okay, so this is again a mathematical simulation of now this system. Okay, and for epsilon equals to 0.1, I'm simulating the trajectory, the backward trajectory of two initial conditions, which are accumulating in this limit cycle, which is the limit cycle provided by the periodic solution provided by the averaging method of order 1. Okay, so now here, just with a first order analysis, we were able to provide information about the existence of limit cycles. Can we continue? Of course, we can continue. Just as before, we didn't have find any periodic solutions in a first order analysis. Then we go to the second order analysis in order to find a periodic solution. Here we have one periodic solutions in a first order analysis, and again we can apply now the second order analysis in order to try to find more limit cycles. And this is a program that can be recursively done. You compute the first order average function, try to obtain informations about limit cycles from this average function, and then you impose some constraints in order to vanish this average function and pass to the next average function, and so step 3, again, we assume minimal conditions on the parameters of perturbation in order to ensure that the first order average function vanishes, and compute the second order average function and its zeros. So note now that f1 is equal 0 if and only if b1 is equal 0 and a21 is equal minus 3a03. So let's check it. We have b1 here. b1 has to be 0 because it's a polynomial in R. Then since it has to be identically 0, then the coefficients of the powers of R has to be identically 0. Okay, so b1 has to be 0 and a21 has to be minus 3a03. Okay, so assuming these constraints, we compute the second order average function, and the second order average function is given by this expression, which is a kinetic polynomial. So we have R that multiplies this factor, and this factor is we call biquadratic function because it's a quadratic polynomial in R squared. Then we can impose the conditions in order that this equation f2 equals 0 has 0, 1, or 2 positive simple solutions. Okay, so for a specific example, let's take g1 as this cubic polynomial and d2 as this cubic polynomial, and b2 equals 1. We get that this polynomial, the second order average function, becomes pi r divided by 4 multiplied by r power to 4 minus 5r squared plus 4. And this is to see that for this average function, second order average function, r1 star equal 1 and r2 star equal 2 are two positive solutions of f2 equal 0. Okay, so for cubic perturbations, the second order average method provided the existence of two periodic solutions. The first order provided the existence of one periodic solutions, and the second order provided the existence of two periodic solutions. Okay, so R1 and R2 are periodic solutions of the difference equation. They transform the difference equation, which converges to R1 star 1 and converges to 2 when epsilon goes to 0. So we get the existence of two periodic solutions of the second order difference equation. One that the norm converges to 1, and the second such that the norms converge to 2 as epsilon goes to 0. Okay, so I have also run a mathematical simulation for this situation. So This is the difference equation that I'm assuming, that I consider in here, that satisfies the previous hypothesis. And we have one limit cycle here, which is an unstable limit cycle, and a second limit cycle here, which is an stable one. Okay, so I have simulated some backward trajectories, the trajectories and forward trajectories of 3 initial conditions in order to see these accumulating regions here. For this simulation, I'm assuming that epsilon is equal to 0.1. Okay, of course, when epsilon goes to 0, then the averaging method is ensuring that this periodic solution converges to a cycle, well, a circle. It's terrible, my circle, but you know, a circle here with radius 1 and another circle here okay, with radius 2. Then when epsilon goes to 0, this limit cycle is deformed into a circle with this radius. Okay. Okay, Thiago, perhaps we should have a break now.
Let's have a break, Douglas. Thank you.
Okay.
Any questions or doubts? No comments? No? Douglas, can we restart?
Yes.
So please.
Okay, thank you. So let's go back for a minute to the formula of the average functions. Okay, so notes that here we need to compute the m derivative of fi minus j. So here fi minus j has to be m differentiable. Okay, and moreover, I'm computing the integral of this derivative. So it's interesting, not to avoid any problem, that this function is actually belongs to the class of Cn of differentiability. Okay, so it's m differentiable and the m derivative is continuous. Okay, m is an index which is at most j. So fi minus j belongs to this class of differentiability. Then if I change this name, this index, n equal to I minus j, then we see that j is equal I minus n. So fn here needed to be in this class, I minus n. Okay, for each n, fn should be ci minus n. Since I'm computing these functions for I up to k, then we see that fn belongs to this class of differentiability. So this is the minimum class of differentiability, such that this integral can be computed without any problem. Okay, so the question is, how is the lesser regularity context such that this formula still provides informations about bifurcations of periodic solutions? Okay, because here we call that we are assuming that all those functions are smooth. but it's interesting to see if it works in less regular contexts. Okay, so this is the content of the next theorem. Averaging method for studying periodic solutions of Lipschitz continuous differential equation. So instead of the smoothness of the differential system that we have assumed, let's assume that the function fi belongs to the class ck minus I differentiability, and in addition, that the k minus I derivative of fi is locally Lipschitz in the second variable, and also that R is a continuous function locally Lipschitz in the second variable. Then, under this condition, this standard form, we can just assume that it's locally Lipschitz in the second variable. It's continuous locally Lipschitz in the second variable. Each one of the perturbations has some regularity, but the differential equation itself is continuous locally Lipschitz in the second variable, because I'm allowing this less regularity assumption for the remainder. Okay, so the result that I'm going to show is that the average functions that we have defined by the formula is still can be used to provide informations about the bifurcation of periodic solutions in this context. Okay, so again, denote f0 equals 0 and let L be the index of the first non-vanishing averaged function. Okay, that can be computed without any problem in this context. Okay. Now assume that for Z star in the domain such that FL vanishes at Z star, assume that there exists a neighborhood satisfying a neighborhood of Z star satisfying that FL is distant from 0 for every Z in the closure of V minus Z star, and that the Brouwer degree of FL V0 is distant from 0. Okay, I'm going to introduce this object in a minute. Okay, then the result is that for epsilon sufficiently small, the difference equation 1, but now in these conditions, admits a t-periodic solution phi t epsilon converging to Z star as epsilon goes to 0. Okay, so this is the averaging method applied for study periodic solutions of Lipschitz continuous equation. However, here we have to consider another kind of hypothesis instead of the simple solution that we were considering in the previous theorems. So let me just introduce the concept of the Brouwer degree. So the Brouwer degree is a function which tries to answer the question f(x) equal y0 for y0, for x belonging to a to some domain. Okay, so we want to know if this equation admits solutions in V. Okay, so that is the context where the Brouwer degree is defined. The Brouwer degree is an object that provides an answer for this question, and this is defined by some abstractive properties. And let me show these properties, and then I show a formula for the Brouwer degree. So let's consider a domain Rn, a counter domain Rn, and let V be a subset of X open and bounded. And consider a continuous map which is defined in the closure of this set V. Okay, and also a point in the counter domain which does not belong to the image to the image of the boundary of this bounded subset. Okay, then for each triple f, v, and y0, we can define it an integer, okay, denoted by dB, the Brouwer degree of f, v, and y0, having the following three properties. The first one is exactly which answer this question. If the Brouwer degree of v, f, v, y0 is distant from 0, then y0 belongs to the image of v by the function f. That is, there exists an x in v such that f of x is equal y0. That means there exists a solution for this equation. And another property is that the Brouwer degree of the identity is equal to 1. A second property, which is the excision property, we say that it states that we can decompose the Brouwer degree into sums of Brouwer degree under some hypothesis. And the third property, the most important one in order to do computations, is the invariance under homotopy of the Brouwer degree. So let's consider an homotopy, a continuous homotopy between f0 and f1. These functions are defined in the closure of V through the homotopy, and let yt be a curve on the counter domain. Okay, defined for t between 0 and 1, and assume that yt does not belong to the image of the boundary of V during the homotopy. Okay. Then the result is that the property says that the Brouwer degree of this homotopy is constant in T. Okay, so when I have a function and I want to compute the Brouwer degree of this function regarding a point in the counter domain, not in a subset of the domain, we can try to find another function which is homotopically equivalent to the function that we want to study, and then to compute the Brouwer degree. That's what we are going to do. Okay, and the Brouwer degree is uniquely defined by these three properties. Okay. Okay. So that's what I was saying. If we have, for instance, a function, okay, and we can prove that this function is homotopically equivalent to another function, just that behaviors in a more nicely way, then we can use this new function. Let's say this is an homotopy between these two functions. We can use this new function in order to compute the Brouwer degree of the first one. Okay. So in the smooth case, if f is a C1 function such that the determinant of the differential of f is distinct from 0 for every x in the inverse image of y0 by f, then the Brouwer degree can be computed by this formula. So it's just the sum of the sign of this determinant. This is this distinct from 0, then it has a sign. So it's the sum of the signs varying x in this inverse image of y0. Okay, so this formula implies that if z star is a point in X such that f of z star is equal to 0, and this determinant is distinct from 0, so if this determinant is distinct from 0, then the function f it can be seen as locally a diffeomorphism. It's a local diffeomorphism. Then this 0 is an isolated 0 of f. Then we can apply this formula, because the sum is just, it's not a sum, it's just the determinant, and we can apply this formula in order to obtain that there exists isolating neighborhood of z star such that the Brouwer degree is distinct from 0. Okay, so this means that in this theorem, if the average function FL is smooth, even if the difference equation is not smooth, it's just locally Lipschitz, then if FL is smooth, then we can just looking for simple zeros in order to conclude the existence of periodic solutions by the theorem. Okay, so let's go back to the example, but now with a Lipschitz continuous perturbation of these harmonic oscillators of this second order differential equation. So now B is the same we were considered before, and G now is assumed to be Lipschitz. Okay, just Lipschitz. Performing the first step, which consists in transforming the system into this periodic non-autonomous system, okay, we can compute now the first order average function. Okay, it's just substitute. This is a general formula for the first order average function. Okay, and now let's consider a more specific example. So we saw that in the continuous case, if we have a quadratic perturbation, then the first order average function does not provide the existence of periodic solutions. Okay, so in this less regular context, let's consider a piecewise quadratic perturbation. G1 as beta plus times y squared for y positive and beta minus y squared for y negative. Note that this is continuous because it's 0 for y equals 0, and also Lipschitz because it's continuous piecewise differentiable. Okay, the graph of this function, something like that. Let's assume that, for instance, beta plus is positive and beta minus is negative, just to draw a picture. So this is something like that. Beta plus y squared and other branch here, beta minus y squared. It's beta minus negative. And if beta minus is positive, it's something like that. Okay, so in this situation, it looks like a cubic. Okay, and we see that just like as the cubic perturbation, after a first order analysis, in this case, we obtain information about the existence of periodic solutions. Okay, so for computing this first order average method, of course, we have to split this integral into integrals. Okay, but it is the usual thing, and this I have to integrate this for the theta where this is positive, and then for the theta where this is negative, just in order to change beta. Okay, so this integral is equal to b1 pr minus the integral between r to pi of beta plus r sin of theta power to 3 minus now the integral between pi and 2 pi of the same function, but now with beta minus. When we compute this function, remember that in the quadratic case, this vanishes. But now, since we are changed beta, we get this function, okay? And it admits a simple zero. So, assuming that this value is positive, then the equation F1, oh, this should be in boldface. It's not other function. Then the first order average function. Okay, so assuming that this constant is positive, then this equation F1 of R equals 0 has a unique positive solution given by this value. So in this case, with less regularity, the first order averaging method, that is now theorem 2 for L equal 1, provides the existence of a periodic solution converging to R star as epsilon goes to 0. And going back through the change of coordinates, we obtain the existence of a periodic solution of the initial, the second order difference equation, such that the norm of this periodic solution converges to R star as epsilon goes to 0. Okay, so allowing non-differentiability in the perturbation, we can work with polynomials of lower degree and find periodic orbits. Okay, so this is another mathematical simulation of an example of this kind. G1 is just like above, and I'm assuming that beta 1 is equal 1 and beta 2 is equal 2, and the red dots here denotes initial condition, and I'm drawing the backward trajectories of the differential system, this one. Okay, for epsilon again equal 0.1. Okay.
So Douglas, I have a comment, short comment, just to relate this with my lectures. If you can you show the F1 function? In this case, as you have non-regularity, you lose the symmetry, and then the function does not depend on R squared as previously. And this is like in the Hof in the near the origin, when you study the return map, is exactly the same. It appears the coefficients in all the powers, and this is why in the piecewise world you have also more limit cycles, and also this is the same phenomena here.
Yes. You get more coefficients in the first order average function. In your case, you get more Lyapunov coefficients, right? Okay, so here we have dropped the conditions about the smoothness of our differential equations, and we still can use the formula that we had introduced before in order to produce and study limit cycles and periodic solutions of our systems. But how about if we consider only continuous difference equation? I don't want to consider now Lipschitz difference equation, just continuous. Can we use the averaging method to say something about bifurcation of periodic solutions? Okay, that's the question. So this problem has been approached before in a paper by Jaume Gibra and Buica, and then with one of my students, we have obtained some similar results, and also for high order perturbation. So let me explain a little bit about these results in this non-regular context. Okay, so now let's consider again differential system given the standard form for applying the averaging method, but now I want to assume that the function f is continuous. Okay, I'm not assuming that it's differentiable even in the parameter of perturbation. I'm not assuming that this is differentiable in epsilon. For instance, usually it's assumed that f t, even in the continuous situation, it's assumed that f is equal to f1 of tx plus order epsilon. However, this implies that f is differentiable in epsilon. Okay, so I'm not going to do this assumption. Okay, we are not assuming that f tx epsilon is equal to f1 tx plus higher order terms in epsilon, because this implies that f is differentiable in epsilon. Okay, in this situation, for this first theorem, I'm not going to assume that. And even in this case, okay, I could compute the average, the first order average of the right-hand side of the difference equation. Okay, just taking this function, h1 of z is equal to 1 divided by t times the integral between 0 and t of the right-hand side of our difference equation, fsz 0. Okay, this is the first order difference equation. And the question is, this function still provides information about bifurcation or persistence of periodic solutions for the difference equation 9 for epsilon sufficiently small? And the answer is yes. So this is the theorem. Let z star be an isolated zero of the first order averaging function, and assume that there exists a neighborhood v of z with the boundary, the closure of v contained in the domain, and such that the first order averaging function is distant from 0 for every z in the closure of v minus z star. That's the same hypothesis before. And also that the boundary degree of h1 v0 is distinct from 0. So this is the same hypothesis that I have made before in the Lipschitz context. Okay, so then for epsilon sufficiently small, the difference equation 9 has a t-periodic solution phi t epsilon, satisfying that phi t epsilon belongs to the closure of v for every t, and that phi, this periodic solutions, converge uniformly to a constant function as epsilon goes to 0. Okay, so this is the first order averaging method for continuous and only continuous differential equations in the standard form. This theorem in this context is proved here, but it has already been appeared in this paper, however, in this context, okay, but it's not actually important for the technique that have been employed there. Okay, so notes that I'm going to show an idea of this proof, okay, but before, notes that here I'm using just, let's say, the first order terms of this perturbation in order to investigate conditions for the existence of periodic solutions. Okay, because here I'm computing this integral for epsilon equals 0. So the question is there a way we can, even if, for instance, if we assume that this function can be written as power series of epsilon, still not assuming differentiability in the variables t and x. Okay, suppose that f is given as a power series of epsilon. Okay, can we use these functions in order to produce and explore conditions for the existence of periodic solutions for this differential equation? That's another question. So consider this standard form. Here there is a problem because it must have an epsilon multiplying everything. Okay. So assume that this function is given like this, and consider now the average function of order I as 1 divided by t multiplied by the integral of between 0 and t of fi now. Okay, it's the same in this context. H1 would be the integral of f1, and now define hi as the average of fi. Okay, if we come back to the original formula in the smooth context, we see that hi, let's put hi here. Hi is equal 1 divided by t multiplied by the integral between 0 and t of fi t z ds. Up to this constant, up to this factor, which does not play any role actually, this function hi is the first part of the formula of the average function. So what I'm going to show is that we can use this part of the average function in order to obtain, to produce conditions for the existence of periodic solutions. Okay, so this is the theorem that I'm going to state now. Okay, so we define our average function and we shall assume this hypothesis. This hypothesis is a little bit strange in the context of periodic solution, but it's a very natural hypothesis in the context of operator equation. I'm going to show it in a minute. Okay, so this hypothesis is the following: the hypothesis H. There exists epsilon 1 such that for each lambda between 0 and 1 and epsilon between 0 and epsilon 1, any t-periodic solution of this difference equation that belongs to the closure of V must be entirely contained in V. Okay, so any periodic for each epsilon and for each lambda here, any periodic solution of this difference equation which is contained in the boundary of V must be contained in the interior of V. V is an open set. Okay, so what I mean is, what this hypothesis means is that we cannot have periodic solutions in V that touch the boundary of V for every lambda and epsilon. Okay, so this is a very strange hypothesis. It may be very hard to be satisfied and verified. However, I'm going to show an example where we check this hypothesis and some remarks of geometry effects that implies in this hypothesis. But it's a very natural hypothesis in the context of operator equation, you see. So the theorem is the following. Denote again H0 equal to 0 and let L be the index of the first non-vanishing average function, but now for this average function, and assume that Z is a point in the domain such that HL of Z is equal to 0, and that there exists a neighborhood of Z star such that the boundary, the closure of V is contained in the domain. HL is distant from 0 for every Z in the closure of V minus the 0 of HL, and that the hypothesis H holds for V. Okay, hypothesis H depends on an open set. Okay, and that the Brouwer degree of HLV0 is distant from 0. So the hypothesis here is almost the same, the hypothesis that we have previously stated in the other theorems, but here we are also assuming this hypothesis H. Okay, then the result is the same. For every epsilon sufficiently small, the difference equation 10 has a t-periodic solution phi t epsilon, satisfying that it belongs to the closure of V for every t, and that it converges to a constant function uniformly as epsilon goes to 0. Okay, so some comments about this, the hypothesis H. Okay, some comments about the hypothesis H. In order to verify hypothesis H, it's interesting to assume its negation and try to obtain a contradiction, an absurd. Okay, so let me just state some things that we get when we assume that hypothesis H is not satisfied. Okay, so hypothesis H is saying that for each lambda in 0, 1 and epsilon in 0, epsilon 1, any t-periodic solution of this difference equation belonging to the closure of V must be entirely contained in V. So when we assume its negation, we obtain numerical convergent sequences epsilon m and lambda m, because it must be true for every epsilon lambda. So it's the negation implies the existence of sequence epsilon m and lambda m, epsilon m belonging to 0, epsilon 0, and lambda m belonging to 0, 1, such that epsilon converges to 0 and lambda m converges to some lambda bar in the closed set 0, 1, the closed interval. It also provides a sequence of t-periodic solutions x, m, t contained in the closure of V and t-periodic solutions of this differential equation. Okay, because hypothesis H says that every periodic solution containing in the closure of V must be entirely contained in V. So its negation provides periodic solutions of this difference equation which are contained in the closure of V, such that there exists an instant, a time, Tm belonging to 0t, such that xm of Tm belongs to the boundary of V for each m in n. Okay, so we get periodic solutions of this difference equation contained in the enclosure of V, but such that it reaches the boundary of V at some instant, at some time. Okay. In particular, we get that xm of t is equal to this because xm is a solution of this difference equation. Then we have the integral characterization of solutions of difference equation. So it's equal to its initial condition plus the integral of the right-hand side of this difference equation. And since it is t-periodic, when we compute it at the period t, capital T, it must coincide with xn evaluated at 0. It must coincide with its value, with its initial condition. And since epsilon m and lambda m is distant from 0, we conclude that the integral of this function between 0 and capital T is equal to 0. And this is an important fact in order to check that hypothesis H holds. Okay, and in addition, as an application of the Arzelà-Ascoli theorem, we can assume that this function is uniformly convergent to a constant function that belongs to the boundary of V. Why is that? Well, this can be assumed by the Arzelà-Ascoli theorem. This can be assumed to be uniformly convergent, but since for every n, xn must breach the boundary, so if this is uniformly convergent, then it must converge to a constant function in the boundary. Okay? Well, this is the negation of hypothesis H. Remark 7 provides a nice geometric condition that is not equivalent to hypothesis H but implies hypothesis H. Okay, so if we assume that the boundary of our open set V is a smooth manifold, then hypothesis H holds provided that there exists an epsilon1 such that for each z in the boundary, z in the boundary of V, this vector ftz epsilon is transversal to the boundary of V at z for every time and every epsilon in 0 epsilon 1. So why is that? Let's consider, for instance, that V is a sphere. Okay, it's the whole ball. It's a ball. Okay, and the boundary of V is this S2. Okay, so here I'm supposing that this vector is transversal to this boundary for every t and epsilon and in each z. So suppose that we have a solution, not periodic, but suppose that we have a solution that starts inside V and eventually reaches V at some point. It's hard to draw it with. Okay, it reaches. It's inside the ball, but reaches the boundary of the ball at some time, and then it comes back to the interior of the region V. So at this point, if we draw the tangent space of the boundary of V at this point, let's call this point by P. So P is equal to phi of t hat epsilon. Okay, at this point, if we compute the tangent vector, of this trajectory, it belongs to this tangent space. So if this happened at this point, and for some t and epsilon, this assumption do not hold. Okay, so if this is true, then this cannot happen. We cannot, it's not just about periodic solution, but we cannot have the trajectories of our differential equation, solutions of differential equation that reach the boundary and then continues and then goes back to V. If it reaches the boundary, then it must leave and crosses it transversally. Okay, so this is a geometric hypothesis that implies, in particular, that our hypothesis H is satisfied. Okay. Okay. So I think that I have 10 minutes. Okay, I have 10 minutes. I think that I can prove, give an idea of the proof of a more general result that implies our theorems, and Friday I can comment about an example, an application of the theorem. Okay, so in order to prove these two theorems, we had proved a more general theorem that involves what we call it by full average function. Okay, so we define this h of z and epsilon as being the average of the right hand side of the differential equation. Okay, I'm not computing this for epsilon equals 0. And for this, for this average, full average function, we have this result. Assume that for a given open subset V, such that the closure of V is contained in D, hypothesis H holds, H of Z epsilon is distinct from 0 for every Z in the boundary of V and epsilon in 0, 1, and that the Brouwer degree of H for some epsilon, okay, for some epsilon, V0 is distinct from 0 for some epsilon, okay? So under this hypothesis, we have that there exists for each epsilon 0, epsilon 1, there exists a t-periodic solution of the differential equation 10, satisfying that this is contained in the closure of V for every t between 0 and t. So this is a general averaging method. Okay, I'm not computing the first or second averaging method. I'm just computing the average of the right-hand side of our differential equation, and we can conclude, we can obtain this theorem. So how can we prove the theorem? The proof of this theorem is based on the second approach that I have showed for you in the first lecture, the operator equation approach. Let us recall this operator equation approach here. So we define X as being this Banach space, the Banach space of continuous function defined on 0t and with image in Rn, such that for x of 0 and x of t coincides. Okay, so it starts in a point, and for t equal the capital T, it coincides with the initial position. Okay, so it starts in a point and at the same point, the same image. And Y is the Euler space of continuous functions such that x of 0 is equal to 0. X and Y are Banach space with the subnorm. And we have a V, okay? And with this V, we denote this subset of X omega as being the functions in X such that it belongs to V for every t in 0t, okay? This can be seen to be an open bounded subset of X, okay? And we define the linear map, the same thing that we have done Monday, L, a linear map between X and Y, just by taking the difference between X evaluated at t and X evaluated at 0. This is a linear map. We note that the image of L is actually equal to X intercepted with I, because the image L of xt is a function that vanishes for t equals 0, because I'm subtracting X of 0. And we can see that this image is actually closed in Y. And in addition, the kernel of this linear map is just the constant functions. Okay, so it's this space, the kernel of L, can be identified with Rn. Okay, so as I have commented in the first lecture, a function x can be continuously extended to a t-periodic solution of the differential equation 10 if and only if it's a solution of the operator equation, because this is equivalent to say that x of t is equal x of 0 plus the integral between 0 and t of epsilon f s xs epsilon ds. I'm seeing that here I didn't define an epsilon, but this is an epsilon of x computed at t. Okay, so we also define this projector. It's just some technical things that we have to define in order to apply proposition. So don't care if it does not make any sense, but it will work. So we also define this projector in y, which is given just by computing the function at t and dividing by t. Okay, so again, the image of this projector is can be identified with Rn. Okay, so this is the result we used in order to prove our general averaging method or general averaging theorem. This result is actually an abstract continuation result for operator equation, which is stated here. And this is I'm just rewriting this result. The theorem is exactly the same, but for this operator equation here. Okay, so the proposition says, let L and epsilon and Q be like above, this operator that I have defined, and assuming that the following conditions are verified for every epsilon between 0 and epsilon 1. H1 is L epsilon is distinct from lambda any epsilon x for every x in this space. I'm not going into the details of this hypothesis, but it is equivalent in this context of our hypothesis H. Okay, so hypothesis H, I said that it's a natural hypothesis in the operator equations context. That's because it came directly from this hypothesis. Okay, second hypothesis, Qn epsilon is distinct from 0 for every x in the kernel of L intersected with the boundary of omega. So kernel of L are the constant functions, and the boundary of omega are functions, if we see this definition, are functions such that for some t between 0 and the capital T, it belongs to the boundary of V. Okay, so since it must belong at some point in the boundary of V, and the kernel of L is the constant function, so these intersection are just points in the boundary of V. Okay, and a last hypothesis is that the Brouwer degree of this function is distant from 0. Okay, so under this hypothesis, three hypotheses, the operator equation 13 admits a solution in the closure of omega intersected with the domain of L. So the hypotheses of our general averaging method are stated in order to this hypothesis to be satisfied. So hypothesis H implies hypothesis H1 directly. Condition 12, which is the condition 12, condition 12 is this one. H z epsilon is distant from 0. Condition 12 will imply condition H2 directly, because Q any epsilon, when we apply Q any epsilon and we substitute the definition of any epsilon, the definition of Q, what we get is exactly Hz of epsilon. Okay, so this implies, this hypothesis is implied by condition 2, because I'm assuming that this is distant from 0, so that is exactly condition H2. And condition H3 will be verified, will be a consequence of this condition. Okay? So, since Q n epsilon of x is equal to hz epsilon, when we compute this Brouwer degree, I just have to compute the Brouwer degree of our full average function. Okay? And since this Brouwer degree is distant from 0 for a specific epsilon star, we can use some topological method, some topological argument here that involves the fact that the Brouwer degree is piecewise constant and some connectedness and compactness topological argument. We can show that this Brouwer degree actually is distant from 0 for every epsilon between 0 and epsilon 1. So hypothesis H3 also holds for the operator equation. And therefore, from proposition 4, from proposition 9, we get the existence of a t-periodic solution of our difference equation such that this periodic solution is contained in the closure of V for every t. So we prove this theorem, this general averaging method. We have proved this general averaging method. And as a consequence of this general averaging method, we obtain both theorems. Theorem 1, okay, in this context, we can always check that hypothesis H is true, and theorem 5, we can apply theorem, the general averaging method, and try to use the Brouwer degrees of these higher order average functions in order to compute this Brouwer degree, okay, and obtain the existence of a periodic solution. Okay, so I think that it's enough for today. I think I'm going to finish here, and Friday I'm going to start explain an example of the theorem, which is a non-Lipschitz continuous perturbed harmonic oscillator. Okay.
Okay, Douglas, thank you. There are some questions or comments. No. So thank you, Douglas.
Thank you.
And chill. We continue